Hello friends, welcome to this lecture. Myself Amlan. Today I will discuss about pure rotational spectra of a diatomic molecule. We know that total energy of a molecule in the excited state is E equals to EE plus EV plus ER, where EE is the excitation energy of an electron in a molecule. EV is the energy due to vibration of the molecule, and ER is the energy due to rotation of the molecule. Okay. Now, pure rotational spectra arises when only the rotational energy ER changes during the transition. Now suppose the electronic energy EE of a molecule remains unchanged. In addition, we assume that the vibrational energy EV of a molecule also remains unchanged. This is possible if we assume that the two atoms of a diatomic molecule are as if joined together by a rigid rod, so that the distance between them remains unchanged as the molecule rotates as a whole. Such a model of molecule is known as a rigid rotor model. Okay. Now suppose this is an atom of mass m1 and this is the atom of mass m2. Okay, and they are joined together by a rigid bar of length r. Now let C be the center of mass of the composite system. Now suppose r1 be the distance of the first atom from the center of mass, and R2 be the distance of the second atom from the center of mass. Okay, so we may write R equals to R1 plus R2. Now since the molecule rotates end over end about C, so we may write M1 R1 equals to M2 R2. Now solving these two equations, we get R1 equals to M2R by M1 plus M2, and R2 equals to M1R by M1 plus M2. So the moment of inertia of the molecule is I equals to M1 R1 square plus M2 R2 square. Okay, so this is the moment of inertia of the molecule. Now if we put the value of R1 and R2 from this equation, then we get this is equals to M1 M2 by M1 plus M2 into R square. Now this can be written as this is equals to mu R square, where mu equals to M1 M2 by M1 plus M2. Mu is called the reduced mass. Okay. Thus, the rotation of a diatomic molecule is equivalent to that of a single point mass mu about an axis distance r from it. Okay. Now if omega be the angular velocity of rotation, then the angular momentum L of the molecule is L equals to I omega. Okay. So this is the angular momentum of the molecule. Now here L is quantized. So we may write L equals to root over J into J plus 1 into H cut, where J equals to 0, 1, 2, 3, etc. J is called rotational quantum number. Okay. So J is called rotational quantum number. Rotational quantum number. Now, the rotational kinetic energy of the molecule is E equals to half I omega square. Now, if we put the value of omega from this equation, then we get E equals to L square by 2I. Now, if we put the value of L from this equation, then the value of rotational kinetic energy becomes E equals to H cut square by 2I J into J plus 1. Now H cut equals to H by 2 pi. So we may write this is equals to H square by 8 pi square I into J plus 1. Okay. So E is this. The molecule can thus have a discrete set of rotational energy levels with different value of J, and this constitutes the pure rotational energy level. Okay. Now we draw the pure rotational energy levels of a molecule. Okay. Now we draw the pure rotational energy levels of a molecule. Suppose this is J equals to 0 level. This is J equals to 1 level. This is J equals to 2 level. This is J equals to 3 level, and so on. Now here selection rule is delta J equals to plus minus 1. Okay. Now here allowed transitions are transition occurs from J equal to 0 level to J equal to 1 level, J equal to 1 level to J equal to 2 level, and J equal to 2 level to J equal to 3 level. Also from this level to this level, this to this level, and this to this level, and so on. Okay. So these are the allowed transition. Okay. Now, as in the case of atomic spectra, the energies of the different molecular levels are expressed by their term values. Okay. Now, term value equals to E by Hc. So we may write E by Hc equals to H by 8 pi square Ic into J plus 1. Now let this is denoted as Fj. So we may write this is equals to Fj equals to, now let this is denoted as B. So Fj equals to B J into J plus 1, where B equals to H by 8 pi square Ic. B is called rotational constant. This is rotational constant. Okay. Where J is 0, 1, 2, 3, and so on. So this is term value. Now the difference between the term values of two levels gives the wave number of the emitted or absorbed spectral lines due to the transition between two levels. Okay. Now the difference between term values of two levels gives the wave number of the spectral lines. Okay. So now here selection rule is delta J equals to plus minus 1. Okay. This is our selection rule. Now applying the above selection rule, we get the wave number nu bar equals to delta Fj. Okay. This is equals to Fj plus 1 minus Fj. Okay. Now the value of Fj plus 1 is B into J plus 1 into J plus 2 minus, and value of Fj is B J into J plus 1. Now here this is equals to B J plus 1 common. So this is equals to J plus 2 minus J. This is 2B J plus 1. Okay. This is equals to 4B when J equals to 1, and this is equals to 6B when J equals to 2. So the spacing between two consecutive rotational lines is independent of J and is given by delta nu equals to 2B. Okay. Thus, pure rotational spectral lines are equispaced. Okay. Now we draw the equispaced pure rotational absorption spectral lines for the HF molecule. Now we draw the equispaced pure rotational absorption spectral line of the HF molecule. Suppose along this axis we draw nu, that is wave number, in centimeter to the power minus 1. Okay. And along y axis, this axis we draw absorption. Okay. Now for the HF molecule we get this type of graph. We get this type of graph. Okay. This is for j equal to 0, this is for j equals to 1, this is for j equals to 2, 3, 4, 5, 6, and this is about 100 centimeter to the power minus 1, this is about 200, this is about 300 approximately. Okay. So this graph is the pure rotational spectra, absorption spectra for the HF molecule. Okay. Now here in this diagram, the value of delta nu, that is wave number difference, is found to be 4050 meter inverse. Okay, in this case. Now, according to the electromagnetic theory of light, rotational motion of only polar molecules like HCl, HF, etc. lead to the emission of radiation, because in such molecules the center of positive and negative charges are permanently separated, so that they possess permanent electric dipole moment. And in non-polar molecules like nitrogen, oxygen, etc., the center of positive and negative charges are coincident, so they do not possess any permanent electric dipole moment. Now, according to the electromagnetic theory, rotation of a dipole can lead to the emission of radiation. So, there will be emission of radiation due to rotation of only polar molecules. Now, applying Bohr's correspondence principle, we conclude that even in quantum mechanical case, pure rotational spectra arises only in polar molecules. Okay. So, only polar molecules shows the pure rotational spectra. Thank you for watching this video.